let me just flip over my screen. Now guys, if I am going to revise certain things and rewrite stuff, you might run out of room. So if you've got some lined paper at the ready, that might be a good idea. So, Hendrik Lorentz was investigating the forces involved of charged particles moving with a certain velocity, and it turned out that we've got like 3 different vector quantities all in different directions. So that's where the right hand rule is useful, because if you hold out your hand, then your palm is going to point orthogonal to the plane of your thumb to your fingers. So you've got your XYZ axes on your hand. We're going to use the convention, okay, that your palm is going to be the force. I realise this has nothing to do with solenoids. I'll get to that. I think I may have jumped the gun. Your fingers are always pointing in the direction of the magnetic field. Your fingers always wish to point from north to south of an external permanent magnet. Okay, I will say that term all the time. They're trying to go from north to south. Now, sometimes they don't actually get there. If it's a radial field that goes around in a circle, there is no North Pole and South Pole. Your thumb is always the flow of positive charge. We call it conventional current. This guy was around making up these rules before they knew about electrons. When they were doing this, they thought there was positive charge flowing through copper wires. And then 20, 30, 40 years later, they go, actually, it's electrons are going the other way. But it didn't matter, because a positive charge moving right is very analogous, it's the same as a negative charge moving left. Okay? So they didn't need to suddenly make a left-hand rule. It still works. If you ever have a negative particle, then your thumb has to point in the opposite direction. Okay? So, this was an electron traveling to the right. Aha, my thumb must point left. Okay? So if an electron's moving right, my thumb points left, our fingers are pointing into the page. And so the instant that it enters the field, remember out here, there's no external magnetic field, there is no Lorentz force. As soon as it crosses into the magnetic field, suddenly there is a force. This force is at right angles to its motion, so it doesn't do any work. If it had a little component in the direction, it would gain energy. If it had a little component backwards, it would lose energy. But it is at right angles, so it doesn't change the speed. The kinetic energy does not change, but the direction is constantly changing, and that's what circular motion is. You've got a constantly changing velocity with a constant speed. And so you can imagine this now. As you bend your thumb around to track the trajectory, your palm is always pushing towards some central point. That's your center of curvature. Okay? And as I said, it produces a circular motion because the force is always at right angles. Then, obviously, once it leaves the field, no more centripetal force, it travels off with a straight line. Okay? In Unit 4, we can equate the centripetal force with the Lorentz force, and we get this lovely equation down here. But it would make sense... don't worry, we'll do it later. Term 3 stuff. Okay? Let's just go back a page because I want to answer the solenoid question. And if we spend 20 minutes looking at solenoids, I am not mad about that. So, way back to the start of our magnet. Remember, the field lines of a magnet always want to go external from north to south. We don't draw field lines inside the magnet, but really these loops, theoretically, these loops all connect, right? Every loop would go through the magnet. Well, we can't really measure the magnetic field inside a magnet because there's atoms and stuff stuck in the way. So we don't worry about what's going on inside. All right? The right grip rule Again, I'm going to use the right hand is going to be used for 3 separate rules. All right, and in every single rule, your thumb is going to be conventional current and your fingers are the direction of the field. Okay, so the Oersted apparatus, which has been packed away, this was Hans Christian Oersted, noticed that when he passed current through a wire, a nearby compass, map compass suddenly moved. And what it was doing is it was aligning itself with the magnetic field produced by the wire. Now, it turned out to be much larger in field strength than the Earth. The Earth is on the order of 10 to the negative 5 Tesla. And so he was producing a much larger magnetic field. And so the magnet went, you know what? I'm going to align myself with the net force rather than just the Earth. Okay? And so then he noticed that when he flipped the current, the magnet changed direction. So the direction of the field was associated with the flow of conventional current. Okay? So in this diagram, on your page, whatever page it is, 21. None of you seem to be on page 21. That's okay. Your thumb points upwards, and your fingers are going to curl around. Now, this is an oblique view where you can see all 3 dimensions. And so what I would have done is I would have said, let's look from below. If I looked down here and looked up the wire, I would see current travelling away from me. So let's draw that. Let's change our orientation. Okay, my thumb points into the page. And from this perspective, your fingers are going to be rotating around clockwise. Okay? There's another way to look at it. I could look side on. So over here, this could be side on of my electrons. Oh, I made it electrons. So if I had a diagram of a wire with electrons travelling right, instantly my thumb must point left. So hold out your thumb, point it left. Curl your fingers so that they're underneath the wire. Your fingers are pointing out of the page, so that's the direction of the field below. Rotate your fingers so that they're above the wire. They're going into the page. So you would draw X's. Now, electrons spread themselves out nice and evenly. That's Kirchhoff's law. They don't group up, they don't bunch up and spread out. There are no compressions or rarefactions. So an even flow of charge, stop that, would have a nice regular magnetic field. You're not going to find that there's a strong field here and a weak field there. So remember, you have to draw your symbols nice and evenly spaced. Okay? The Biot-Savart law tells us about the strength of the field. So can we go to page 24? So obviously, the further you get from the wire, the weaker the influence, because it has to travel to a greater distance and occupy a greater volume. So the field strength does decrease. And that's why we've got the 1 on R, okay? So in this diagram, remember, R is the distance from your wire. So really, it depends on 2 things. How much current is flowing and how far you are from it. Remember that mu naught it's just a physical constant. It's in your data sheet. It's called the magnetic constant, okay? And it's 4 pi times 10 to the negative 7. So those are the 2 factors. And it's highly likely that you will be assessed on this kind of question because it involves everything. You've got current and distance to determine magnitude. These are also vectors, so they can combine. Let's do a nasty question. I've just come up with an idea. Find some spare paper, please. Find some spare paper. Spare paper. Here's an example. We have a current travelling this way of 5 amps. And 10 centimetres away is another wire where current is travelling down with 6 amps. So 2 wires, maybe they're in a wall, maybe they're in a machine or something. Okay? And I want us to figure out what is the net magnetic field strength at point A, which is a distance of 4 centimetres from the right wire. Therefore, it's going to be 6 centimetres from the left. Okay? So what you're going to have to do is combine the magnetic field produced by the left wire and combine it with the magnetic field produced by the right wire. Now, are they working together? Are they opposing? First off, let's use our right grip rule. So, the left wire, get your thumbs out. On the left wire, it's producing it into the page. Just remember that. Okay, let's look at the right wire. Oh, look, at point A, it's going into the page. So we could say that in between the two wires, they're working together. Yeah? This is very similar to the solenoid. Imagine a loop of wire, and we said inside the solenoid, they're working together. That's why you get really, really strong magnetic fields inside your solenoid, because all of the wires are working together, and so you get a very high density of field lines. All right, that's good. Maybe I would assign a convention that into the page is positive. Out of the page might be negative, but it turns out we don't have to worry about any out of the... Maybe I'll put a point over here in just a moment. So, we could do that the sum of the magnetic field is B, let's call this left and right. B from the left wire plus B from the right wire, and we're simply going to add them together. Now, I could be cocky and factorise out a common factor, but let's just say it's going to be mu naught I over 2 pi r plus mu naught I over 2 pi r. Yeah? Do we want to factorise out mu naught over 2 pi? Yeah. Yeah, let's do it. Mu naught over 2 pi bracket I over r plus I over r. Just remember, doing it this way, we will never know what each individual wire produces. We're just going to find the result. If you left it like this, you could go, oh, this one produces so many Tesla, and oh, this one produces so many Tesla, and then you can compare them. But by doing it this way, we're not going to know. But let's go. Mu naught in your data sheet. Is it? I'm hoping I'm not mistaking my constants. Okay, the left plus the right. So we'll go, now here's, you've got to be careful. We've got to make sure that we match the radiuses with the corresponding currents, because you've got 2 R's and 2 I's. You need to make sure that they're paired up. So maybe I will colour code my red pen is going to be 5 amps over 0.06.
Is this a hard question, sir?
Nah. Section 1, 6 marks. Maybe 5 marks. You got the equation, you've got to use it, but can you see it's assessing a lot of stuff? Right grip rule, the Biot-Savart law, vector additions, convention, all of that's being combined into a question.
Could it be like a part A or part A draw the field line?
Yeah, we might want to draw these field lines as well. It'd be pretty tricky.
What direction would the current need to go for it not to go into the paper?
If they're both travelling parallel, then they would cancel out in the middle, because one wire would go into the page and the other wire would come out.
And could you then figure out where to put the particle so it has no net force?
Oh, you're speaking my language. You're singing off my hymn sheet. That would be an extension question. I imagine it's doable. We could have a go and see if we get anywhere. Does anyone want to solve that for me?
4.67 times 10 to the negative 5.
And it's got a direction will go into the page. Okay? I've become really conscious about how many times I pick my nose, or I wipe my eyes, or I'm like adjusting my contact lenses. It's like, shouldn't be doing that, should I? Where's our? Did everyone disinfect themselves prior to?
65 cases in WA now. So.
And 63 of them are at Christchurch Grammar. Am I right? say. I don't know. All right. Okay, let's try it on the other side now. Now, two things are happening. If I go outside, I'm increasing my distance from the right wire. And so its effect is going to be less. But over here, they're going to work against each other. So let's just pick. This would be, part A, for example. Part B, let's choose point B, which is, 0.05 meters. Okay? So now, I'm 5 meters from the up current, and 5 centimeters from the up current, and now I'm 15 centimeters from the down current. But let's just figure out what each is doing. So let's look at the left wire. Get your right hands out. Now, the left wire is producing an out of the page, and the right wire is producing into the page. So they're fighting each other. So we have to assign a convention. One has to be positive, one has to be negative. And it would probably make sense that the left wire wins because you are closer to it. All right? The further that the wire is, the less effect because of the inverse proportionality. So, let's just remember that. Let's do part B under here. We could say that the sum of the magnetic field is B left plus B right. And I'm going to say that B left equals, right hand rule, out of the page, equals negative. And B right equals, right hand rule, into the page, equals positive. Okay? So just remember that my first term in that expression has to be negative. Again, we could be cheeky and we could factorize out. So we'd go mu naught I left over 2 pi r left plus mu naught I right over 2 pi r right. Mu naught over 2 pi bracket. Now, I left is going to be, I'm going to go negative 5 over 0.05 plus 6 over 0.15. Okay? I hope we can see, I'm trying to color code and highlight things there. So I'm pretty sure the left wire is going to predominate in this fraction because this is going to be timesing it by 20. You're going to get a negative answer. All right? So it's saying that the resultant field strength is going to be negative. It's going to be out of the page. Did you solve it?
Negative 1.2 times 10 to the negative 5.
Do you actually put the negative, or do you...
Well, you have to force it using the convention.
No, but like in your actual answer.
Well, no, never. But your calculator will say negative 1.2
times 10 to the negative 5.
Which we never leave your directions in positives or negatives. You always come back to your convention and go 1.2 times 10 to the negative 5 Tesla out of page. Okay?
So just a quick question.
Yo.
So you have I traveling up the wire and down the wire and the other one. Is I the flow of convection current, or is that just
Well,
flow of current?
if you're not told anything, you always assume conventional. So if this was a diagram, I'm saying that's conventional, that's the flow of positive charge. My thumb points up and down, left and right. Okay?
They usually current flows in the opposite direction.
We know that now. Yes.
They did,
But they didn't when they made this convention. Okay? All right. So, that was an extension, Larry and Alec, that was an extension of the example that I gave on this page, where we just had one wire and we looked at them in different points. So here, electrons traveling right, thumb points left. Above the wire, fingers are going into the page, so A and B into the page and rotate around. Okay? So that would be an extension. It would be to look at two different magnetic fields produced from two different wires, and we've got to remember that they're vectors so that they combine. We express that strength of the vector with lines. Amazing. Did you all do chapter 5.1 for your holiday? Good. I'll check your work later. Thank you. I still haven't spoken about solenoids, have I? No. Get to the point. Do you have some room? Let's draw another solenoid. Guys, I'm pretty much going to redraw exactly the same diagram, but I need you guys now in front of me to commit it to memory. So, let's...
What page is this?
Good. 23. Sorry, my laptop's skipping out. Okay. Now, again, remember, I always draw my my solenoid, I go backwards and then loop around the front. You need to have a little slight obliqueness to determine which way things are flowing. Okay? So this solenoid now has been attached to two cells to make a battery. And always remember that the longer side is positive. The smaller side is negative. That will then allow us to know that your positive charge goes away from the positive terminal and towards the negative. That will then also allow you to know from this diagram at the front, our current is travelling downwards. Okay? Now, remember what I said. You can analyse any point of the solenoid, top, bottom, front or back. The right grip rule will tell you what the magnetic field is doing inside and outside. But me, I want to know what's happening outside because I'm going to use the rule that outside they go from north to south of a permanent magnet. So, let's pick the top. At the top, I'm going to draw the current travelling out of the page. It's just a dot. Okay? So at the top, my thumb points out of the page. Boom! Fingers pointing left. Done. That's it. Outside, they move left. Inside, they move right. That's all I need. All right? So I draw in my wire. Here we go. Ready? Boom. Pow. Done. Almost. Now, if it asks you to draw the field lines, you'd need to draw a bit more just to show a conservative field. But if all it's asking for is which side is north and which side is south, then I just want one loop. Because remember what I do now? I'm going to hide my solenoid and go, let's pretend that this is a magnet. All right, and I throw my iron filings around my magnet, and don't we remember that field lines always go from north to south? That's it. I've now identified which side of my solenoid would be a north pole and which side of my solenoid would be a south pole. Done. Okay? But we're not going to put the galaxy there, are we? What have I done? Go back a bit. So remember, all field lines, external bar magnet, go from north to south. Okay? Now, to make this a bit trickier, here's what they would do. I'm just thinking if Mr. Murray wants to make an exam question, let's go back a notch and go... A student places a permanent bar magnet as shown. They then close the switch. Which way would the magnet travel? Is it go... Well, yeah, we know now. Let's pretend I did this at the start. You go, will the magnet stay there? Will it be repelled away from a north pole, or will it be attracted to a south pole? Okay? So now we've just added an extra order of complexity here. So not only do we have to identify the poles of our solenoid, we then have to figure out whether it's going to push the magnet away or attract it towards. So, same deal. I go, all right, let's do something different now. Let's analyze the front of our solenoid. So everyone get your right hands out put your thumb down, because now you're a wire at the front of the solenoid. Now, behind my thumb, my fingers are in the solenoid, they're travelling right. If I rotate my thumb out, now they're in front of the solenoid and they're travelling left. That's all you need. As soon as you've done that, you can sketch your field lines. Inside, outside. Okay? And we know that field lines external to a permanent magnet go from north to south. Here we would have a repulsion. Okay? The magnet would be drawn away. Which I think is what Larry was correct, but from my perspective he had it wrong because he pointed the wrong way. No, it's going to go that way. No, it's going to go that way. It's going to go that way. Eh? Because we're facing the wrong way. You get that sort of mirror effect. So Larry was correct. Okay? So yeah. Did you all do that validation where I gave you the diagram of the solenoid?
Yes.
Larry did.
I only last year.
Huh? Do you want to do it now?
Yeah.
Shall I chuck it up on the screen?
Yeah.
All right.
Might as well, sir.
Yeah. Oh, wait, there it is. Oh, here we go. What? Have a go. I haven't printed it out because I'm not really well prepared. Oh, so now this is going backwards. So now you've got to start with the polarity and then work your way backwards to figure out which way the current must be flowing.
What's this? What's this? What's this?
I think I broke it. All right, so remember the statement. External field lines of a permanent magnet go from north to south. So if you remember that statement, we've got our first answer here. We go from north to south. All right. Now we've got to label, you've got to use your right grip rule to figure out which way the current's flowing in the coil. So again, I would say pick the front wire. Pick the front wire and align your thumb so that the field's travelling in the correct direction. So straight away for this, I would go, let's look at this front wire here. Thumb points up. Oh, look, inside the solenoid, they're travelling left. Outside the solenoid, they're travelling to the right. If you pick to the top, you go, okay, oh no, that's not working. Oh, there we go. Thumb points in. Above the solenoid, field lines travel to the right, rotate it around, and underneath they're travelling left. So that's what I would do. Right grip rule has enabled me to identify. Oh, jeepers. Why did that happen? Why did that happen? Why did I change the thickness of my red pen like... Boom! Okay, so at the front we're going up, curving it around, and you can see that even this diagram, they've tilted the solenoid slightly so that you can figure out which wire is at the front and which wire is at the back. Okay, now we need our polarity, not our electric polarity. I know that my positive charge is going to be attracted to the negative terminal and repelled from the positive. Okay? Fun? All right. What was I going to ask Mr. Angus to set up for this class? Got the wires over there. No. We've got time. I'm not in much of a rush now. We start.
Does something do with that?
The solid, not... As long as you stay at your desk and no food or drink or music, talking. Let's go over here. I just destroyed this. Okay. In year 11, during electricity, students would go why have I got a negative on my multimeter? And I just say, shut up, don't worry about it. But now you can actually use the colouring of our power packs to figure out the red is the positive side, right? And so our electrons, our positive charges are going to be repelled from the positive side. So my thumb is going to come out of the red side. It's going to go through the switch. It's going that way. It's then going to return by the return wire back to the black. So when I turn this switch on, I know that my thumb's pointing that way, right? Now, if I turn this on and the wire is suddenly forced upwards, are we ready? I'm only going to do it 3 times. Ready? Whoa! Lorentz force pushed it up. Which way must the magnetic field have been in the region of that wire in order for it to be pushed upwards? That way. Yes, that's the right answer. It must be pointing that way. We'll say towards the window. Okay? So that now enables us to figure out this is a U-shaped magnet, right? There's a pole here and a pole here. In between, field lines must have been travelling that way. From what pole to what pole? North to south. So this side is north, that side is south. So in between, we have an external magnetic field to the wire, an external magnetic field that's travelling towards the window. Okay? If I did this, are you ready?
Oh my God.
What way would the wire get pushed?
Down.
Down. Yes. Look at this. You guys are going to smash the way in there. All right. So the paper. We'll just do one. The wire would get forced downwards. That makes sense. Let's use our right grip rule now. Okay. The current is still travelling to the right, but now my field lines are travelling out from the window, and so the Lorentz force on the wire is going to be down. Are we ready? Whoa. Okay. Cool beans. What one last thing can we flip? The flow of charge. So okay, I've got my fingers going from north to south, away from the window. Now I want to change the direction of my current. Now this is bad technique because you always want red to red, black to black. But I can reverse the polarity. Red to red, black. I can reverse the polarity now, and so now I'm flipping the direction of my thumb. So now we're going to go back to being pushed upwards. So if we followed now the positive charge is travelling around the return wire and now travelling left through the horseshoe magnet. Okay? And so now it should jump upwards. Okay, so up jumps the wire. Are we all happy with that? Cool. The Lorentz force is going to be equal to BIL. So we need to know the magnitude of the current. We would need to know the length of the wire that's within the external magnetic field, and we would also need to know the magnetic field strength. Okay? Let's go back to some spare paper. We don't Mr. Murray story time. I just want to see if I've got some spare paper to draw. Ooh, force between. Here we go. We don't have any room, unfortunately. No. Oh, okay. Find some spare paper. I'm just going to go to the right side of page 29. Okay. The easiest way to do that is Lorentz force F equals BIL. But we've got, Ethan, Larry, we've got the magnetic field produced by the magnet is interacting with the magnetic field produced by the current carrying conductor. Now, we already did this, and you can see that I've attempted to sort of draw a combined magnetic field. Let's draw it again to get good practice at this. So I'm going to draw in the horseshoe magnet. You don't really need to draw in the horseshoe magnet. But this is from my perspective. I was looking that way, and here was our little north, and here was our little south. And so our field lines are going to be doing that. And we're going to draw them nice and uniform. Nice and parallel between. All right? We're then going to have to try and combine that vector representation with... Now, I want the field thumb point, I want it going into the page. Up, I want it forced upwards, so I want my thumb going into the page. We're going to have to then take this wire and remember, right grip rule. So, thumb goes into the page. I'm going to draw clockwise radial fields getting further and further spaced apart as I get further and further from the wire. All right, I'll just draw 3 for now, or I'm going to run out of room. Now, this is the biggest, for me, this is where I struggle the most. I need to combine those two fields to produce a net magnetic field. Yeah? So off to the right, I'm going to, call that B1, call that B2. Over here, I'm going to draw B1 plus B2. Well, what can we do? We can look at the regions where they're working together is underneath the wire. So if I imagine taking this wire and sort of taking this diagram and sliding it down into that region. Underneath, you would see lots of lines. You would have a large field strength. Above the wire, you would have left meets right, and they would cancel. Okay? Now, a student did email me, and I've placed it in the AMA, you do get a slight bending downwards. So I'm going to look at this diagram here. This is a perfect diagram that he found. I hadn't seen this before. Google imaging. This is what I'm saying. We're going to combine the fields. Imagine this was rotated around like that. Okay? I don't know. Can I rotate this diagram? Probably. Anyway. Combining those two, you get this kind of shape. But in the WACE exam, that's what the marking key did. Again, upside down. So can you see the WACE marking key didn't put the bump in? So theoretically, that's true. There should be a slight downwards bump, but the WACE didn't really care. Okay? So I want you guys to, if this ever occurs, I don't know what year this WACE... Oh, hang on. 2018. Okay. So... we're 2 years removed from the 2018. Will they ask you to draw a net magnetic field again? Maybe. Okay? So, let's go back to trying to draw. Where's my combined magnetic? Here we are. So, if you haven't already, combine them on your page, please. We'll just draw the wire for now. We don't really need to draw in the bar magnet. Now, one thing that the WACE exam did is they made a loop like that. So sometimes you do see a loop like that. No, sorry. A loop like that. Was that what the answer was? Make sure I've got it right. Closer above, further apart below. So that's really, if you look at the marking key, closer above, further apart below, the overall shape consistent is basically saying that it's symmetric. So if we sliced it, we would get that kind of shape. And obviously the lines need to be traveling in the right direction. Okay. But I would even say, even something like this, you get a wire slightly above and then it decides to bump below like so. Something like that would be fine. Yes?
The field lines coming in from the side need to be like equidistant bar?
Technically, yes, but then you're combining that with that. So this is why it becomes really tricky. Well, here's the thing. Could I ask you all now, once you've done that, get your laptops out, Google image. As I said, you could give this question to 20 different physics teachers they would all draw 20 different diagrams, but they're all following the same rules. More lines below, less above. One teacher might have a loop. You show me your wallpaper? It's lovely. And they're travelling in the right direction. So, what are we going to Google search? I said this before. Dipole electric field lines, parallel plate electric field lines. If you Google image, you'll find a whole different variety from a whole different heap of source. What would we say here? Net magnetic field. If you just Google image, things like net magnetic field, wire and magnet. Combined field lines. And you probably don't make tests and exams too often, but you can sometimes, if you click on one of the images, then it brings up similar images, and you can go down different sort of rabbit holes of you find an image, and then there's like 20 other images like it. So you can sort of travel through Google Images, and if you get the right kind of diagram, then you can find different diagrams similar to it. So show me if you find something. What do you got there? Ooh, go back. Full screen that bad boy and show all of our friends. Thank you. All right, so you get things like that. Okay, that is one interpretation of a wire in a magnet combined. Okay, Larry, full screen it. Show us. Show and tell. We'll get on the big blue button. I'll give you moderator. What do you call it? Presenter status. What do you got? All right, I'll pay it. See that bottom line sort of bends upwards. What it's analogous to this. So this is sort of, the more correct would be to do something like this. Okay? But as I said, the WACE exam didn't do that bump. They went the other way. Right, so, yep.
If you did the bomb in the WACE exam, would you?
You have to pay it. You'd have to pay, because that's probably from a reputable website, physics.org or hyperphysics.net. There's a lot of reliable websites out there that would correctly show it. Yes, Larry?
Why does it bump?
Why does it bump? You've got left from the field, but then the wire on this side, the wire has a downwards component, doesn't it?
Yeah.
So the wire has a downwards component that isn't cancelled by the horizontal. But the horizontal wins because it's got a stronger left than the wire has right, so it wins by going left. But then it's downwards.
Yeah.
So it's a bit weird to think that the wire was making a right and down, but the net magnetic field is left and down.
Yeah.
Okay? And then over on that side, the opposite. It's got an upwards. So, again, you'd have to quickly draw in your down arrow and your up arrow. So that's why it sort of divots downwards.
So why did the WACE do it the other way?
Who made the marking kit? Some fat old dude from another school. Anyone else find some cool images? That's my one recommendation to you guys. Google image search the orientations of magnets, bar magnet, magnetic field lines, combined magnetic field lines of wires and horseshoe. The more you see, and then if you get some crazy question in the exam that asks you to draw it, you're going to be more likely to succeed. Okay? Alrighty. I think I'm glad that you're back. I had my classroom over in it. It was all set up. I had my additional monitor. I had my weights in the corner. I had my clothes. Had my food. I had my external keyboard with my mouse, my little Bluetooth mouse. It was good. I had my YouTube videos. I had my Netflix. I had to dismantle it all yesterday because the school's returned. All right. I'll think about setting up some more demos for us tomorrow, but we're pretty much getting good with the right grip rule, the Lorentz force. Okay?
Thank you.
Catch you guys tomorrow.
Thanks, sir.